Hi, my name is Marius. I'm a PhD student in the University of California, Santa Barbara, and I will talk about action-guided kernel fuzzing today. This work is a collaboration between UC Santa Barbara, University of Minnesota, and EPFL. The kernel is a very elemental part of today's devices. It's the management layer between hardware and applications. As such, its security is crucial for the security of the whole system. Google recognizes this and runs its fuzzing infrastructure syspot on several Unix-like kernels 24 hours a day, 7 days a week. Even with this efforts, many bugs go unnoticed. Only 2 years ago, some researchers found a bug that has been in the Linux kernel for 15 years. And a few weeks ago, actually, there were also 2 new privilege escalation bugs detected in the Ubuntu kernel, which left many users at risk. Because of this, we still need to work further on vulnerability detection on kernels, and coverage-guided kernel fuzzing is a state-of-the-art technique for doing so. Coverage-guided fuzzing usually starts from a seed corpus or an empty corpus. You then go ahead and select the seed and mutate it, or you generate a new seed from scratch. The output of this stage is what we call a fuzzer program. It's just a sequence of system calls and arguments. This program is then executed against the target kernel, leading either to a crash showing some problem in the kernel, or it executes successfully. We can collect coverage and use this coverage to discard the program or add it to our corpus. On a high level, this is how most current state-of-the-art fuzzers work. They're coverage maximizing. They want to find as much coverage as possible. This is good. It's been shown to be very effective, but it's also not perfect. In our observation, especially bugs such as memory-related bugs need 2 specific constraints to be met before they materialize. Look at a double free, for example. It only materializes if both frees are in the same memory buffer. If they're on different ones, they're just unrelated and it's not a problem. An uninitialized read, on the other hand, requires an allocation and then immediately a read from this memory. If there's a write in between, we initialize the memory and it's not a problem. Especially the second constraint is what is easily overlooked by coverage. We can also see this from a concrete bug in the Linux kernel. This use of the free bug works in the following. We first allocate a file descriptor, and we then issue the create ID command, allocating a RDMA ID private struct. With the next command, destroy ID, we free this struct, and finally, with the listen command, the kernel tries to add some element to a list inside of the struct. This, of course, triggers the use of the free. The problem here is that the pointer to the struct was not removed from a management structure. And now, why do coverage-guided fuzzers struggle to find this bug? To find this bug, you need to use the system calls in an unintended order. But at the same time, if you use system calls in an unintended order, the kernel may see this and exit out on a shallow error path, leading to very low coverage. This, in turn, seems uninteresting for the coverage-guided fuzzer, and it goes ahead and explores different areas, potentially missing the bug. Because of this, we propose to change how we generate and mutate programs. On a high level, we look for system calls that interact through some shared memory, and then we vary the order in which they are called. Before we can get to the technique, I want to get 2 definitions out of the way. First of all, darts. So we have this program, a sequence of system calls, and then we start executing the first system call. It triggers certain operations in the kernel, for example, an alloc, a write, or a free. At the point of this alloc, we have traversed certain functions and have a current call stack. These 3 items put together is what makes up a dart. A dart captures which system calls trigger what actions with their context. As a picture, just like throwing a dart, we execute the system call hoping to re-trigger the same action. I've talked about action so far a little bit. An action is a high-level operation with some semantic meaning. We define it through its type, address, and size. The last 2 are very intuitive. For an allocation, for example, it's just the start address and the size of this buffer. The type in our prototype is restricted to heap-related actions. So we have allocations, we have deallocations, and some reads and writes. Let's get to the actual technique now. Action-guided fuzzing is a novel technique to synthesize potentially bug-inducing programs. This contains 2 steps. First of all, action mining. Here we collect darts through coverage-guided fuzzing and then analyze them for relations based on some shared memory. The result, what we call groups, is given to the program synthesis, and we then use it to generate potentially bug-inducing system call sequences based on predefined templates. We have templates for these 7 common vulnerability types, but we also offer a DSL for the ability to extend these templates. So how does action mining work? We start with coverage-guided fuzzing, and we record all these accesses in the kernel, these starts, and then we learn which system calls trigger what actions. With this information, we now want to find relationships between system calls. So we look for system calls that access the same shared memory object, and this allows us to solve the first constraint, the spatial constraint. The result of this is what we call groups of system calls, groups of darts, and we give this to the program synthesis. The first step of this analysis is grouping. When we recorded these darts, we now take only the darts from one program. To find out whether or which of these darts work on the same memory buffer, we can just look at the address. And in the example on the slides, of course, this leads to 2 groups. These groups are now given to the next step, merging. Here we take the groups from different programs, and we want to see which of these programs operate on the same logic buffer. Since we're not looking at a concrete buffer anymore, addresses are not useful. We decided to use the stack trace, the context information. If 2 darts have the same type and the same stack trace, they work on the same logical buffer, and we can merge the corresponding groups together. We now have a group of darts that all work on the same logic buffer, and we can use this for the program synthesis. The program synthesis is there to solve the temporal constraint. We use templates which define the order of actions that need to be performed to trigger a certain bug. For use of the free, for example, this would be alloc, dealloc, and then some kind of use. After we chose the template, we choose a group randomly that offers all the required darts. Of these darts, we then choose a dart randomly, and now since every dart has a system call and argument associated with it, we can immediately generate a program. And this program now can be executed against our target kernel. We implemented this technique in our prototype actor based on a well-known coverage-guided fuzzer syscaller. We evaluated according to several questions. I will talk about the following 3. Are the darts actually able to re-trigger the action we previously recorded? Is actor able to generate more bug-inducing programs than syscaller? And are we able to find new bugs? We performed this evaluation on our development kernel for the metrics, and for the bug finding campaign, we used long-term support and stable kernel versions. Since we record the darts on one kernel state and re-execute them on another, we need to check that they are actually able to re-trigger the action we previously recorded, because a changed kernel state can lead to a changed behavior. In our experiments, we are actually able to do so in more than 50% of the time. Allocations are even more successful in doing so. We can intuitively see why this is the case. After an allocation succeeds, it needs to be stored somewhere, say for example in a linked list. Now the position in this linked list can change, making it harder for subsequent darts to access the same memory buffer and making it more likely for the dart to fail. The next question is whether actor can generate more bug-inducing programs than syscaller. We recorded the programs generated by both fuzzers and tried to match them to our templates. It turns out that across all templates, our fuzzer is actually able to do so more effectively than syscaller. For the more simple templates, such as invalid free, which is just one free, there's not that much of a difference between the 2 fuzzers, but this is not surprising because it's a very, very simple technique. On the other hand, if you're looking at use of the free or out of bounds, these are more complex strategies, and here we can clearly see that coverage-guided fuzzers struggle and our technique shines. Finally, we ran our fuzzer for 10 days on 4 Linux kernel versions, and we found 41 new bugs. Of these, we were able to reproduce 24 reliably, and we reported them to the developers. 11 are still under evaluation, but 13 have been confirmed and 9 have been patched. Of the 41 bugs, 26 are memory corruptions, for example, use of the freeze or double freeze. 11 were discovered through insertions, warnings, or infos, and are therefore most likely due to logic bugs. The remaining ones are segmentation faults. As a conclusion, we present action-guided fuzzing, which is a novel input generation strategy for kernel fuzzing based on action guidance. Action guidance complements but does not compete with coverage guidance. In fact, we rely on coverage guidance to find actions in the first place. We also present Actor, which is our prototype implementation of coverage-guided kernel fuzzing. We evaluate the tool and show the effectiveness through the 6 questions that we answer in the paper. And in this evaluation, we also find 41 previously unknown bugs in well-tested Linux kernel versions. Thank you everybody for coming to my talk, and I'm happy to take any of your questions.